If we have a ray box or a laser and we shine it at a screen, the light is going to diffract when it passes through. If we have multiple slits, it's going to diffract multiple times. The diffracted waves will then interfere with each other and form regions of high intensity and low intensity on the screen. This happens due to constructive interference or destructive interference. Constructive interference happens when two waves arrive in phase and they form a wave of larger amplitude. Destructive interference happens when two waves arrive out of phase, which reduces the amplitude or results in a flatline looking wave. Now, there is an equation we can use to calculate the wavelength of the light from this experiment. If we call the fringe separation, that means the distance between the high regions of intensity x, and we call the distance from the slits to the screen d, and the distance between the small slits a, we can find that the wavelength equals ax over d. Now, you don't need to derive this equation in the exam, you just need to know it. There's also something else that you should know about this experiment, and it's that when the slit separation is significantly less than the distance to the screen, the value of x, the fringe separation, should be determined by measuring multiple fringes and finding the mean. This is because it helps decrease the uncertainty in the final answer. Okay, so let's look closer at the slits. Let's say we had 1,000 slits. We would call that a diffraction grating. And if we had something called monochromatic light, which just means one colour of light passing through the screen, we would get sharp regions of high intensity appearing on the screen because there's so many waves diffracting at once. If we're asked to calculate the slit spacing and we're only given the slits per millimetre, we can do A, which is the slit spacing, equals 1 over the slits per millimetre. Now, over on the screen, we can label the regions of high intensity as the 0th order in the middle, the first order, which is the closest region of high intensity to the 0th order, and the second order, which is the one after that. There can also be a third order and a fourth order as well. And if we were talking about the first order, we would say n equals 1, and the second order n equals 2, and so on. If we look at the angle, for example, between the 0th order and the first order wave, and the 0th order and the second order wave, we can use the equation d sine theta equals n lambda, which is the wavelength. Now, again, you don't have to derive this equation, you just have to know it. If the order is not a whole number, and it's, for example, n plus a half, then it would be a first order minima or a second order minima, which occurs between the orders. And this is when the light or the waves destructively interfere and create dark spots on the screen. Okay, so we have the equation d sine theta equals n lambda. We know the maximum angle is going to be 90 degrees because if it was any more than that, it'd be behind the grating, which just isn't possible. And if we substitute 90 degrees into sine theta, it's going to be 1. So we get d equals n lambda. If we then rearrange this to get n, we get d over lambda. This tells us what the maximum order of the interference pattern is. Let's say we got an answer of 2.8. We would always have to round it down to 2 because we can't have 0.8 orders. Even if we had 2.9999, we cannot assume it would be 3. We'd have to round down to 2.